An air mass is a huge dome of air whose temperature and humidity characteristics remain fairly constant over a horizontal distance. This horizontal distance can extend up to hundreds or thousands of kilometers. Air masses are classified according to the characteristics of their source regions. A source region is the area where an air mass originated. The characteristics of an air mass, such as temperature and moisture content, are acquired from the source region. As we've learned, air masses are classified according to their source regions. Source regions may have one of 4 temperature attributes: equatorial, tropical, polar, or Arctic. In terms of moisture characteristics, they can be either continental or maritime. On a weather map, moisture characteristics are abbreviated C for continental or M for maritime. Temperature attributes are abbreviated E for equatorial, T for tropical, P for polar, and A for Arctic. For example, a tropical air mass that formed over a continent is labelled CT, and a tropical air mass that formed over the oceans is labelled MT. When 2 air masses with different temperatures meet, they normally develop a sharp boundary between them. The boundary area where the temperature difference becomes intensified is called a front. The classification of weather fronts are as follows: cold front, warm front, occluded front, and stationary front. Clouds are often very important indicators of imminent weather changes. When they're observed at various times and regular intervals, even an approaching mid-latitude storm can be recognized. In an approaching storm, a change of cloud structure and type will take place. First, high cirrus clouds appear, followed by high-level cirrostratus clouds and low, thick altostratus clouds. When the storm is finally close at hand, dark clouds will bring high winds and pouring rainfalls. But how do clouds form? Clouds are nothing more than water vapor that condenses on microscopic airborne particles, like dust and sea salt, which then accrete into a visible form. The cloud formations of interest to the mariner are formed in the troposphere. The troposphere is a layer of the Earth's atmosphere that extends from the Earth's surface to about 24,000 feet, 7,300 meters above the poles, and to about 65,000 feet, 19,800 meters above the equator. Clouds in the troposphere are made up of water droplets or ice crystals and can occasionally be a combination of both. The consistency of clouds always depends on the temperature. Clouds are classified by their general appearance and level. Cloud names are cirrus, stratus, and cumulus. To indicate the level of a cloud, a prefix is given to the cloud name, like cirro and alto. Cirro indicates high clouds with bases above 20,000 feet. Alto indicates mid-level clouds between 7,000 and 20,000 feet. There's no prefix for low clouds. Low clouds are found from near the ground to about 7,000 feet. Often you find the word nimbo added to the beginning or nimbus added to the end of a cloud name. This means that the cloud is producing precipitation. High clouds are cirrus, cirrostratus, and cirrocumulus. Cirrus clouds are thin, wispy clouds composed predominantly of ice crystals. Thick patches of cirrus clouds indicate that showers are nearby. Cirrus clouds that are shaped like commas indicate that a warm weather front is coming. Cirrostratus clouds are transparent and show little or no structure. When cirrostratus clouds are increasing and are in a continuous sheet, a warm or occluded weather front will approach, bringing rainy, stormy conditions. You can expect good weather at your location when cirrostratus clouds are not increasing. Cirrocumulus are white and grainy with no shadowing clouds. Depending on the location, these clouds can foretell bad or good weather. In the British Isles, they usually indicate good weather, but in southern Europe, they can indicate bad weather. Mid-level clouds are altostratus and altocumulus. Altostratus clouds are usually greyish clouds that cover part or all of the sky. These clouds are composed of water droplets or ice crystals. At sea, altostratus clouds are an important weather indicator. These clouds can indicate that rain or snow is approaching, associated with poor visibility and huge waves with heavy swell. Altocumulus clouds are a detailed cloud deck of cumuliform clouds. These clouds are composed mainly of water droplets. Ice crystals are only present at very low temperature. When altocumulus clouds are in parallel bands, a warm front with continuous rain or snow can be expected. Altocumulus clouds rising from their flat base indicate heavy showers and thunderstorms. Low clouds are nimbostratus, stratus, stratocumulus, cumulus, and cumulonimbus. Nimbostratus clouds are dark and quite homogeneous clouds. These clouds are associated with heavy downpours, high winds, and sea conditions that are hazardous for small vessels. Take precautions when nimbostratus clouds are in sight. Stratus clouds are grey, thin, and usually featureless. These clouds bring fine drizzle or snow grains and, in certain conditions, fog. Stratocumulus clouds can cover part or all of the sky. Sometimes some holes in the cloud deck can be observed. These clouds usually produce light rain or snow. Stratocumulus clouds that have been formed from degenerating cumulus clouds usually indicate fair weather. Visibility may be reduced when precipitation occurs. Cumulus clouds are cauliflower-like clouds whose contours change constantly. Cumulus clouds can have slight or extensive height. With little vertical growth, these clouds indicate fair weather. With a large vertical extent, these clouds are associated with heavy showers and gusty winds. Cumulonimbus clouds are heavy, dense storm clouds with large vertical extent, up to 13 miles. These clouds are also called thunderheads and bring heavy rain, lightning, and gusty surface winds. They should be avoided. In certain conditions, tornadoes or waterspouts can be expected. A warm front occurs when warmer air glides over colder air. This happens because warm air is generally lighter than colder air. As warm air rises, it cools and becomes saturated with moisture. Clouds form when the moisture in the warm air condenses. Warm fronts are often accompanied by low nimbostratus clouds with rain or drizzle. Because of the rain, the colder air may become saturated and cooled, often resulting in fog formation. If the warm air is stable, altostratus and cirrostratus cloud forms. Conversely, if the warm air is unstable, cumulonimbus and altocumulus cloud forms. The latter clouds produce severe thunderstorms. Let's look at the various types of fronts. A cold front occurs when a cold air mass replaces a warm air mass. Because the cold air is denser and heavier than warmer air, the wedge of cold air pushes under the warm air, lifting it up. The warm air can be in a stable or unstable condition. Within a stable air mass, there's static stability in the lower layers, very little convection, and a low degree of turbulence. In an unstable air mass, static instability prevails, along with greater convection and high turbulence. If the warm air is stable, it can be overcast with rain occurring ahead of the front. If the air is unstable, cloud will form, typically cumulus and cumulonimbus, accompanied by thunderstorms. Occasionally, a continuous line of thunderstorms will form along the front, which is also called a squall line. Squalls may create fierce and destructive conditions such as strong winds, tornadoes, hail, or sleet. Note: a cold front usually moves faster than a warm front. If it's associated with bad weather, you may have little time for safety preparations and course changes. An occluded front occurs when a cold front catches a warm front. There are two types of occluded fronts: the cold occlusion front and the warm occlusion front. A cold occlusion occurs when the air mass behind the occluded front is colder than the air mass ahead of it. A warm occlusion occurs when the air mass behind the occluded front is warmer than the air mass ahead of it. A cold occluded front is normally more severe than a warm occluded front because the rainfall is heavier and higher gusts can be expected during the passage of the front. Typically, precipitation occurs on both sides of cold and warm occluded fronts. Also, the cloud and weather sequences are a combination of characteristics of both cold and warm fronts. A stationary front occurs when a warm or a cold front stops moving. As soon as a front resumes movement, it again becomes a cold or a warm front. When crossing from one stationary front to the other, a noticeable change in temperature and/or a shift in wind direction can be observed. The unequal heating of the Earth between equator and poles causes meridional winds. Due to the rotation of the Earth, winds are deflected to the right in the northern hemisphere and to the left in the southern hemisphere. This movement of great air masses is responsible for the general pattern of circulation of air parcels. But it also generates something else: whirling air masses of high pressure and low pressure cells called highs and lows. Highs are also called anticyclones. In the northern hemisphere, winds blow clockwise around an anticyclone, and in the southern hemisphere, winds blow counterclockwise. The winds on the outer edges of a high blow stronger than they do towards the center. Highs usually move slowly and can remain stationary for weeks. Anticyclones bring characteristically good weather with light to moderate winds. Skies are mostly clear or have thin layers of cloud. Under certain conditions, anticyclones can also cause hazy weather or fog. When a high interacts with a low, strong winds and clear skies can be expected. Lows are also called depressions. In the northern hemisphere, winds blow counterclockwise around a depression, and in the southern hemisphere, winds blow clockwise. Winds blow stronger in the center of a low than they do on its outer edges. Depressions usually travel from east to west and can vary greatly in size, velocity, and strength. They bring characteristically unsettled weather, strong winds, and heavy rainfall. Land has the ability to heat and cool far more quickly than the sea. The temperature between the land and the sea can be different at any point during day and night. This temperature discrepancy between land and sea can develop local winds, also recognized as sea and land breezes. As a general rule, we can say that the greater the difference in temperature between land and sea, the greater the wind. As we know, land masses heat up more quickly than sea masses, especially during the day. As the air heats up, the air parcels begin to rise and create low-pressure areas at ground level. At a height of nearly 600 meters, 2,000 feet, the warm air increases speed towards the sea and replaces the cooler air, which replaces the rising warmer air. A circulation system has then developed, the so-called sea breeze. Sea breezes can occasionally reach more than 15 knots. The converse of the sea breeze is the land breeze. At night, the land mass cools more rapidly than the sea, and the opposite circulation pattern takes place. The air over the land cools, sinks, and raises the pressure. The air over the sea is warmer and continues to rise. In general, land breezes are lighter than sea breezes. Fog can be a dangerous weather phenomena. Fog may form either when there is a lot of moisture near the ground or when the air near the ground is cooled to its dew point. But what is the dew point? Scientifically speaking, the dew point is the temperature to which an air parcel must be cooled, assuming that the pressure and water vapor content are constant, in order for saturation to occur. In simple terms, at the dew point the air contains as much moisture as it can hold. When the air near the ground cools to this temperature, water vapor from the air will become visible as dew on the ground or as fog in the air. When can you expect fog to occur? A simple rule is, when the difference between the air temperature and the dew point is small and decreases, or the difference becomes even zero, you should watch out for fog. Let's have a closer look at how you can calculate the dew point. In nautical publications, you can find tables for calculating the dew point. Here's an example of such a table. In the left-hand column, you find the air temperature in Celsius, and at the top of the table, you'll find the relative humidity as a percentage. We assume that the temperature is 27 degrees Celsius, and the relative humidity is 60%. The intersection of the two figures shows that the dew point is reached at a temperature of 18 degrees Celsius or lower. It's good practice to calculate your dew point at least every hour when you navigate in areas which are known for developing fog. There are four main types of fog: radiation fog, advection fog, frontal fog, and sea smoke. Radiation fog is formed in a clear sky and adjacent to rapidly cooling land. The land will cool the air above it, causing water vapor to condense into droplets. Radiation fog first forms in valleys, and during the early morning it can even expand several miles out to sea. Rivers and estuaries may also be affected. When the sun rises and the land starts to heat up, radiation fog quickly disperses. In situations where the land takes longer to heat up, for example when it's overcast, radiation fog may persist. Advection fog, also known as sea fog, is formed when moisture-laden warmer air blows over colder land or water. When the warm air cools down to its dew point, water vapor in the air condenses and fog forms. Advection fog is very thick and persistent. It will only disperse when there's a change of wind which brings drier air. Frontal fog is usually found ahead of warm fronts and occluded fronts, and behind cold fronts. When warm, moist air rises over colder air, it causes the air temperature of the warm air to fall below its dew point. Frontal fog is not persistent, but can cause obstruction of landmarks. Sea smoke is formed when cold air flows over a warmer sea. The cold air absorbs moisture, and the excess moisture, which cannot be absorbed, condenses immediately into fog. Simultaneously, the air is warmed by the sea and its dew point rises, dispersing the fog. Then the warm air rises and is cooled by the air at higher levels, and fog is formed again. Sea smoke does not persist for a long time. It forms, disperses, and reforms constantly until the air adjacent to the sea is adequately warmed. Before you proceed to sea and while you're at sea, it's highly important to stay informed regarding the current and imminent weather conditions. The latest weather information is crucial for the safety of the crew and the vessel. Severe weather can be avoided and the risk of injury and damage can be reduced. Weather forecasts should be obtained at regular intervals. Let's have a look at various sources of weather information. Before you go to sea, you can obtain weather information from newspapers, TV, and the Internet. When you're sailing near the coast, weather forecasts can be received from certain national weather broadcast frequencies on VHF radio. The broadcasting range is usually up to 40 nautical miles. When you're sailing offshore, you can use a Navtex receiver to obtain meteorological forecasts and warnings at a distance of up to 400 nautical miles. Also, a single sideband weather fax receiver can be of great assistance. Under the right conditions, it has a reception range of 6,000 miles. In addition, you may utilize the satellite communication system to receive vital weather information. In former times, before wind measuring equipment was available, the Beaufort scale was the only device available to determine the wind force. The scale was invented in the year 1805 by Sir Francis Beaufort and officially adopted in 1838. Sir Francis Beaufort sailed for many years in the British Royal Navy as a commander. The first Beaufort scale was originally related to tall ships and their sails. Later on, it was modified to imply the effects of wind on land and sea. Let's have a closer look at a modern Beaufort scale. The scale contains a column with the Beaufort wind force, the mean wind speed in knots, the descriptive term, the state of sea, and the probable height of waves in meters. The column with the probable height of waves in meters is added and displays approximately the wave height that might be encountered in the open seas. Weather faxes provide the latest meteorological and oceanographic information available worldwide. They can be received with a single sideband radio. The following key weather and sea charts are useful to mariners: surface charts, sea state analysis, wind and wave charts, sea surface temperatures, satellite imagery, and ice charts. Satellite imagery provides you with cloud cover and tropical cyclone information. Storms can easily be identified because of the large amount of clouds they produce. Ice charts show mainly location of ice, types of ice, thickness of ice, and known icebergs. Here's an example of a 5-day sea ice forecast. On the right side, you have detailed information concerning the ice. The sea state analysis chart shows characteristics of sea waves and direction of movement. These observations are normally made a few hours before broadcast time. The combined sea heights are depicted in solid contours. The relative maxima or minima combined sea state values are enclosed in a box. The arrows indicate the direction of sea waves. Surface charts provide mariners with the principal tool for a basic understanding of the present and upcoming weather. Let's have a closer look at surface charts, differentiating between the surface weather analysis and the surface weather prognosis. The surface weather analysis shows weather patterns based on synoptic surface observations. They're usually made a few hours before broadcast time. The surface weather prognosis shows future weather patterns on a 12, 24, 36 and sometimes even a 72-hour forecast basis. Here's an example of a 24-hour surface forecast chart. On this chart we can see the isobar lines, warm and cold fronts, the central pressure millibar values of synoptic scale lows and highs, and their position in 24 hours. The 24-hour forecast position for lows are identified with vector arrows and an X, and for highs with vector arrows and an X with a circle around them. Adjacent to the forecast positions, you can find the two-digit pressure in millibars, which in this case is 29, which means 1029 millibars. The wind and wave chart shows characteristics of sea waves and wind. The combined sea heights are depicted in solid contours. The relative minima or maxima combined sea state values are enclosed in a box. Wind speed and direction are also indicated. The wind speed is shown in knots. Each bar indicates 10 knots and each half bar 5 knots. Sea surface temperature charts show mean temperature values for a week, 10 days, or a month. Ice edges are also depicted. Some transmissions also contain sea temperature anomalies. The weight of air pressing down on the Earth is called the air pressure. Air pressure is caused by the Earth's gravity, which acts like a downward force. Pressure can be measured by a barometer and can be recorded by a barograph. Pressure readings can be used to predict storms, low pressure areas, high pressure areas, weather fronts, and wind fields. The barometer is the most useful weather forecasting tool for small vessels. There are two types of barometers, mercury and aneroid. Small vessels most often use an aneroid barometer. Although it's not as accurate as a mercury barometer, it's more robust, compact, and affordable. The aneroid barometer consists of a corrugated container nearly exhausted of air, with a spring inside, along with a lever, pointer, and a graduated dial. When air pressure increases, the top of the corrugated container bows in, and when air pressure decreases, the top of the corrugated container bows out. The lever transmits these changes to the pointer on a dial. Air pressure can be measured in inches of mercury or in millibars, also known as hectopascals. The aneroid barometer needs to be regularly corrected for index error and height above sea level. The index error is mainly caused by mechanical factors, and consequently the aneroid barometer slips from its initial accuracy. You should regularly check the accuracy of your aneroid barometer against a corrected mercury barometer. For information about mercury readings, call any National Weather Information Service. Because the air is denser at sea level than at higher altitudes, you must also correct for the actual height above sea level. Use the table Correction of Millibar Barometers to Mean Sea Level for the altitude correction. This table is available in the Nautical Almanacs. Let's look at how to apply the correction. First, note your barometer reading, the air temperature, and your actual height above sea level. Let's assume that the barometer reading is 1015.4 millibars, the air temperature is 20 degrees Celsius, and your height above sea level is 5 meters. By applying the air temperature and height above sea level to the chart, you see that the correction is 0.6 millibars. Add this figure to your barometer reading. Hence, the barometer reading corrected to mean sea level is 1015.4 millibars plus 0.6 millibars, which equals 1016 millibars. Keep in mind that the greater the height above sea level and the greater the temperature, the greater your correction to mean sea level will be. A barograph is a type of aneroid barometer, and as you see here, the pointer is replaced by a pen. It also has a drum and bellows. Every 7 days the drum makes one revolution. A chart, which is affixed to the drum, is graduated in time on one axis and atmospheric pressure in millibars on the other. The barograph provides a continuous record of the atmospheric pressure. Since the barograph can be affected by environmental factors, its location should be carefully selected. Place it in a position that is, as far as possible, free from vibration, loud noise, jostling and gusts of air. The barograph should be fastened in an athwartship's position so the pen does not leave the paper when the ship is rolling.